Torsional resonance is a very interesting subject that isn't discussed too often, and when it is, it's not explained in an easily understandable manner. That's what I'll attempt to do in this video with the help of an analysis paper published by E-Props. The new propeller from E-Props for direct drive engines, like the Lycoming O-360, is now on the market for experimental aircraft. If you're involved in experimental aviation, like me, you've probably been waiting in anticipation for this propeller. So, what's the big deal? E-Props has propellers on the market for various engine types, and in the light sport market, their Durandal propeller for Rotax 9 series engines is absolutely phenomenal, and I speak from personal experience with it. It's basically a ground adjustable propeller that acts like a constant speed propeller. So unlike conventional ground adjustable or fixed pitch propellers, you get good takeoff, climb and cruise performance. If that sounds too good to be true, check out the video linked in the description below where I covered in detail how it works. So a few years ago when E-Props announced they're designing a propeller for direct drive engines, a lot of pilots and airplane builders have been eager to see if E-Props can replicate their previous successes. It's a big deal because it's quite difficult to make such a lightweight carbon fiber propeller for direct drive engines that is reliable and durable. And it will become clear why that is in a few minutes. The analysis from E-Props publishes the results of extensive testing of torsional resonance on a few different propellers, including their new Ascalon on a Lycoming O-360, which is one of the hardest in production engines on propellers. I'll refer to the analysis throughout this video, but you can also read it at your own leisure. I've linked it in the video description. So let's cover why it's difficult to make a lightweight propeller for direct drive engines like the O-360, discuss the results of the analysis, and then I'll offer my first impressions on the new propeller design from E-Props. Crankshaft torsion is really important to understand if we are to approach the subject of matching a propeller to an engine. The first thing to know is that crankshafts aren't perfectly stiff. They seem pretty rigid, and while you won't be able to twist one with your hands, that doesn't mean they don't twist while the engine is running. They absolutely do. So how does it twist? Well, it twists along its axis. I don't have a great way to illustrate this, but this ruler should do just fine. This is torsional twist, and if you can imagine crank webs coming off this, it should make it pretty clear. This illustration from E-Props perhaps illustrates it more clearly. Of course, at normal loadings, it doesn't twist permanently. It returns to its original shape just like this ruler does. How much it twists depends on various factors. One is crankshaft stiffness. Another is the weight, or rather the mass and mass distribution along the blades of the propeller. This affects the propeller's moment of inertia, which is its resistance to changes in rotational motion. This is a major factor. The heavier the prop, the more it resists instant turning, and the more the crankshaft will twist when torque is applied to it. When a cylinder fires and pushes the piston down, the conrod pushes the crankpin, webs, and crankshaft itself. Since the propeller's inertia resists sudden changes in rotational speed, the crankshaft twists. When it twists, it stores energy in the crankshaft, which must be released. Remember, the twist isn't permanent. It returns to its normal form like a spring. It springs back to its original position and releases the stored energy. As you can imagine, with this happening multiple times per second, it causes vibration. The vibration at the crankshaft is transmitted to the propeller hub and propeller blades and can damage any and all of those components over a period of time if not accounted for. Crankshaft torsional twist can be reduced with stiffer crankshafts and with pendulum dampers. Pendulum dampers don't actually remove or reduce the degree of twist. They reduce the amplitude of torsional vibration at resonant frequencies. We'll cover it briefly in the next chapter. Of course, we should also note that the rear of the crankshaft twists more than the front. Again, the ruler perfectly illustrates that, and that's why longer crankshafts generally twist more than shorter cranks. One thing that reduces the torsion and shocks that the propeller experiences is a reduction gearbox. This is obviously not the primary reason why they are used, but gearboxes absorb the shocks that would otherwise have been transmitted to the propeller. Good for the propeller, bad for the gearbox. But this is why it's much easier to design and manufacture a propeller for gear-reduced engines. They simply don't work nearly as hard as direct drive propellers. Of course, most era engines don't have gearboxes. So now that we got a refresher on crankshaft torsional twist, we need to cover torsional resonance. Torsional resonance occurs when the frequency of the torque pulses from the firing of cylinders matches the natural torsional frequency of the crankshaft propeller system, and this worsens vibration. You'll often see some propellers have restricted RPM ranges they are not allowed to be continuously operated in. Well, the reason for that is torsional resonance at certain RPMs. Operating in resonant RPMs will expedite problems like cracked propeller hubs, propeller blades, fatigue damage in the crankshaft, and generate significant forces on engine accessories like the magnetos. As we've established, when a torque is applied to the crankshaft via the crankpin, the crankshaft twists. It then springs back to its original form, but it doesn't stop at its original form. It overshoots and twists slightly in the opposite direction and oscillates back and forth. Remember, it's like a spring. I'll use this pendulum I built to demonstrate. Push the weight and it travels to the other side and then comes back. But it doesn't stop in its resting position in the middle immediately. It passes toward the opposite direction and then goes back again into the original direction it was pushed in, and so on until it eventually stops. In other words, it oscillates. This is a much exaggerated analogy of the amount of twist a crankshaft experiences, but it conveys the idea we need to understand. If we deliver the next push while the weight is still traveling back, that is, out of phase, it dampens oscillation. But if we push after the weight has reached its highest point and is already moving back, that is, in phase, we are amplifying oscillation and the weight will go higher. By the way, this is close to what a pendulum damper does. Pendulum dampers oscillate out of phase with the torsional vibrations to absorb energy at predetermined frequencies. To a much lesser degree, the same thing happens to the crankshaft. If the next torque from firing a cylinder happens out of phase, when the crankshaft is springing back, it dampens the torsional twist. But if the torque is applied in phase, when it's already started oscillating back into the direction of the original force, it amplifies the torsional twist. When torque pulses arrive in phase with the crankshaft oscillation, the resulting amplification is called resonance. What I'm doing here more or less shows what happens at RPMs where resonance occurs. This can push torsional vibration to dangerous levels. Whether vibration is dampened or amplified depends on engine RPM. It's not necessarily higher RPMs that amplifies it. Resonance can occur at lower RPM as well, and every propeller engine system will have specific resonant RPMs. One factor determining at which RPM peak amplification of oscillation occurs is the mass, or rather, moment of inertia of the propeller. A heavier propeller has more resistance to instant changes in rotational motion, and will thus increase the amount of torsional twisting of the crankshaft. So different propellers will have different torsional resonances on the same engine, as clearly illustrated on this graph. And that is why not any propeller can be used on any engine type, even if it produces the same horsepower. Usually a heavier propeller will have peak amplification at lower RPM, and lighter propellers at higher RPM. And this should already start revealing why lightweight props could be a problem on engines like the O-360. E-Props' analysis graph supports this. The two lighter carbon fiber propellers' amplification both peak at high RPM, while the heavy aluminium and wooden props peak at lower RPM. In the decades past, propellers were made of aluminium or wood and were thus quite heavy. Since heavier propellers move torsional resonances to lower RPM, usually below typical cruise RPMs, they were not that difficult to design and manufacture. But why do heavier propellers move torsional resonance to lower RPM? Simply put, torsional resonance frequency depends on inertia. There's an equation to calculate the frequency, or RPM, where torsional resonances will occur. Frequency is inversely proportional to the square root of inertia, so higher inertia equals lower frequency. In reality, it's more complicated than in theory, but that's what it comes down to. Metal and wooden propellers can also withstand larger torsional amplitudes before damage, thanks to the robustness of their construction. And it also helped that these resonances occurred at RPMs below cruise RPM that don't get used continuously. Then came modern composite lightweight propellers. Lighter propellers have many advantages. A lighter propeller will cause less torsional twist of the crankshaft, but will move peak amplification towards higher RPMs, potentially into cruise RPM or somewhere into the useful RPM range. And while composite materials are very strong, the hub attachment can be a vulnerable point. So if the resonance falls in the cruise RPM range, it can create durability problems. So now E-Props was sitting with a problem. How to get the torsional resonance of their lightweight propeller out of the cruise RPM range. To do this, E-Props had a few things to play with. Firstly, they could make the propeller really light. Doing so moved the resonances even further toward higher RPM, past cruise and toward takeoff RPM, an RPM range which is not continuously used. Being lightweight also slightly reduces the amplitude of initial torsional twist, so the forces getting amplified are smaller to begin with. Apart from that, playing with the mass of the propeller mostly just moves the peak resonance around. Something else E-Props did is make sure the full throttle RPM range, or RPM spread, is smaller. It's easier to move resonances out of a 100 RPM range than out of a 500 RPM range. And this they did aerodynamically. Bear with me on this one, it will make sense in a minute. E-Props really perfected the ESR effect on their previous propellers. ESR stands for Extended Speed Range, and I covered it in detail in the linked video. A conventional fixed pitch propeller has a very narrow speed range where it's effective, and that's due to blade pitch. It can be set with a fine pitch, which makes it great at takeoff, but it will run out of steam as airspeed increases and won't be able to cruise very fast. Or it can have a coarse pitch, which allows the blades to be very effective at high speed, but it will then really struggle at takeoff and even in climb, with some sections of the blades potentially stalled at very low speeds. Most fixed pitch or ground adjustable propellers are set somewhere in the middle for a reasonable compromise, but this means it's not offering great takeoff or fast cruise performance. The propeller thus only excels in a very narrow airspeed range, which likely isn't even in use that much. That's why variable pitch or in-flight adjustable propellers are so great. By changing blade pitch in flight, they're effective at takeoff, climb, and cruise, giving them a very large airspeed range where they work effectively. Constant speed propellers are even better, as it automatically adjusts pitch angle to maintain a selected engine RPM. With ESR, it's possible to extend the effective speed range of fixed pitch propellers close to that of constant speed propellers. You get most of the performance of constant speed propellers at less cost and with none of the complexity. The Ascalon propeller also makes use of this ESR effect. Apart from the performance benefit, this reduces the full throttle RPM spread the propeller is operated in. This is the important part. A conventional fixed pitch propeller has a very broad full throttle RPM range. When initially applying full power for takeoff, the engine RPM can be as low as 2250 RPM, depending on the propeller, pitch, and application. As the aircraft accelerates, RPM increases with airspeed as load on the engine decreases. If we were to leave in full throttle when eventually leveling out, it could potentially go over 2700 RPM, again depending on the blade pitch angle and application. Of course, that's beyond redline on an O-360 and we don't want to do that. But it has a full throttle RPM spread which can be as wide as 2250 to 2750 between static and full throttle level flight. That's a spread of 500 engine RPM that needs to fall outside of all peak resonances. With the ESR effect on E-Props' propeller mimicking constant speed propellers, it's different. It will achieve roughly 2600 RPM at static when initially applying power for takeoff. But RPM barely increases with airspeed due to the ESR effect. In fact, E-Props claim at full power level flight, 2700 RPM will only be reached at about 135 knots. So the Ascalon has a full throttle RPM spread of only about 100 RPM, and at full power during takeoff and climb at roughly 2600 RPM, you are not operating in the peak resonant RPM range. This is significant because torsional twist is greatest at full throttle. That's when the engine is producing maximum torque pulses. So you particularly want to avoid resonances in the RPM range where you're operating at full throttle. Of course, we're not flying at full power continuously, but usually somewhere between 65 and 75% power. And very importantly, with the E-Props, reducing power moves engine RPM into a range of very low torsional resonance. But on the heavier wooden and metal propellers, not only does that wide 500 RPM full throttle spread potentially fall inside these resonant RPMs with massive peaks, but lowering power and RPM in cruise also moves it towards RPMs with much greater torsional vibration. Talk about being stuck between a rock and a hard place. By the way, the engine used for these tests was the O-360 A1D. The O-360 is particularly challenging on propellers. Having only 4 cylinders means it fires only every 180 degrees of crankshaft rotation. That's a very large interval between cylinder firings, making it comparatively rough running. Additionally, it's a 5.9 liter or 360 cubic inch engine, so it has large displacement per cylinder, producing substantial torque pulses. The A1D variant also does not have the pendulum damper. In addition, it has the hollow crankshaft, meaning it's the variant with the most flexible crankshaft that will twist the most. So E-Props made sure their propeller can withstand probably the worst variant of an engine that is particularly harsh on propellers. E-Props claims a 2000-hour TBO, which strongly suggests they successfully mastered torsional resonance. That's it for torsional resonance, so let's shift focus to something else about the E-Props Ascalon. By just looking at it, we can deduce at least one thing. The most notable property of the prop is that the blades has quite a lot of sweep. This accomplishes mainly two things. First, it improves propulsive efficiency at high airspeed. This is because of the angle the blade tip slides through the air. The higher the sweep angle, the lower the effective Mach number. This is because sweep reduces the component of velocity perpendicular to the leading edge, which delays shock formation. I discussed sweep in great detail in my previous video about the prop fan or open fan engine. Even if you have zero interest in that, there's a lot of information on propellers in there, so I highly recommend giving it a watch. I won't cover it in detail in this video. Sweep is also often used to lower noise. Normally, sweep also indicates that the propeller is targeted at high speed efficiency at the cost of low speed efficiency. Sweep typically involves a compromise. I asked this question of Jeremy from E-Props, and his answer was that it's not a one-size-fits-all propeller. For example, with their offering for the 180 horsepower O-360, they specifically optimized the 2-blade Ascalon for faster machines and the 3-blade for stall type applications. However, that doesn't mean the 2-blade will be poor at takeoff and the 3-blade will suffer at high speed cruise. It utilizes the ESR effect, which will hide most trade-offs and be efficient across the speed range. So I don't expect we'll see the typical low speed efficiency compromise of sweep thanks to the ESR effect and the purpose-designed blades for each application. Another impressive feat is the weight of the propeller, coming in at just 7 kilograms or 15.5 pounds. I don't have many propellers lying around that I could weigh for comparison, but the Macaulay 2-blade metal prop coming off our Continental O300 weighed 13.5 kilograms, just less than double. And the O300 is a 145 horsepower engine, so a metal prop for the 180 horsepower O360 would be heavier still. But I simply don't know yet how it will perform in real life, though I do hope to get my hands on one to test. Let me know in the comments your thoughts on the Ascalon and how they gave it superior resonance characteristics. Thanks for watching, see you in the next one.